Okay, good afternoon, and welcome to EE16, the 8th lecture on circuits. So we're going to wrap up on the capacitive touchscreen. We're going to talk about scaling up, right? A touchscreen doesn't just have one place where you can touch and it detects that, but there's lots of places and you can detect the touch everywhere. Then we're going to deal with this issue that a colleague of you pointed out, that our circuit actually doesn't work because these triangles, they do not always necessarily hit zero. So we'll deal with that. Current source, we are not going to deal with today. We are going to start a new topic called op-amps, or actually it stands for operational amplifiers, but that's way too complicated a word and too long to say, and especially too long to write. So we generally simply use the shorthand op-amps. And there we are going to talk about various basic concepts, feedback, very important, ideal operational amplifiers, ideal op-amps, and then we talk about the first circuit that uses an operation amplifier. Okay, so scaling up. So what do I mean? Well, what we designed so far, what we designed basically a touch button, we could call it. And I've shown you a little demo or so. There you can put your finger in the right spot and it will detect that, and maybe there are other spots where you can put it also. But if you have a screen like a smartphone or so, then you would like to be able to detect touch anywhere on the screen, and you would not only want to detect that the screen has been touched, but of course you want to know where the screen has been touched. So our basic touch sensor worked on the idea that we had basically a conductor, and we had another conductor in the perpendicular direction, and then there was a section in the middle here that was a capacitor. We called that one C0. And then when we put our finger on this thing, well, we get additional capacitors. We call them C finger 1 and C finger 2, something like that. And the total capacitance is going to increase because of that. Okay? So now we're going to just put a lot of these in order to scale up, have a lot of these sensors. So we make this strip much longer. And we're going to add additional wires if you want, like this. As many as you like. I'm not going to spend the rest of today's lecture drawing wires. Okay, and so every crossing now could be considered such a capacitor where in principle we should be able to detect touch. So if now I put my finger anywhere here, well then it will detect, the finger is there close by or over one of these. Typically you put these very close together so that you don't have spots where it doesn't detect anything. Right? Okay, so how would you read this? Well, you leave it like this, and then you're going to connect a sensor between any two nodes. So let me just say sensor, capacitance sensor between any two nodes, basically the sensor with this current source and so on, and the comparator that we designed. You connect it there, okay? And then, of course, you detect touch here. Then afterwards, you remove this connection here and you put it here. Well, you would detect this one. And then when you want to detect the other column, you connect over there, right? So you can cycle through the entire array, and one by one you read out every capacitor. Of course, you got to do this pretty fast. If somebody's playing a game and moving their hand very quickly, you want to be able to detect that. And so there are various, electronics is fast, and then you can do some parallelization and stuff like that, but we get the concept. So scaling up actually isn't particularly difficult. So the next little topic that we want to talk about is this drift business. So, when we designed our touch sensor, we had, as a function of time, used a function. This is called a function generator, and you can build it, for example, with a microprocessor, or you have one in the lab. And this put out a current I of t, and that current was like this. Actually, I shouldn't have made this. Was like this. Okay? There's a square wave. This is called a square wave. And there was a value plus I0 during one phase, and then during the next phase it would go minus I0, and then it would switch again to plus I0. Okay? We used that. Why did we use this? Well, because then we applied this to our capacitor. So basically what we had is, we had this current source, I of t, that has this square wave characteristic, and we applied this current to our unknown capacitor. So this is C, question mark, Vc of t. Okay? And Vc of t now, we sort of expected that when in this particular, here the current is positive, so the voltage is going to increase because our capacitor acts as an integrator, and then the current is negative in this part here, so the voltage is going to ramp down again, and this continues like that. Okay? So why did we use this balanced square wave? Well, because we want to always start at 0. Okay? We want to always start at 0. If this thing starts drifting, goes away from 0, then we had used this comparator, right, to detect whether touch was present or not, and then we are going to make errors. It's not going to work very well. So we always need to go back to 0. Now, one of you pointed out absolutely correctly that that's probably not going to be the case for our circuit. Why is it not going to be the case? Because it's a touch sensor, and the value of this C question mark of the touch capacitor is going to change. That's the whole point of the circuit. When you put the finger there, it's a larger capacitor. Remove the finger, you have a smaller capacitor, and that makes it that this slope here is sometimes this, and sometimes it's going to be less when the capacitor is larger. Right? And so it could be that the slope is going to be less because here you had your finger there, and then afterwards you removed your finger. So now the slope is again going to be faster, like this one, and so you end up here. And then of course in the next phase this simply keeps the memory, and maybe you have something that gets you back to 0, but most likely Murphy's law or whatever tells that it's not going to work, right? You cannot rely on this going back to 0, and of course, I mean, I exaggerated here perhaps a little bit, but this is not going to work. We got to fix this, okay? So there is another reason also. There are several reasons why this kind of thing is going to happen and why we should expect this. And one other one that is sort of easy to understand that we're going to use in our analysis is that if, let's say, the minus I0 was a little bit larger than plus I0. And in practice, that always is going to be the case. The instrument that you have in the laboratory is very expensive and very precise, but hey, nothing is perfect. Okay? So it's going to be a little bit different, and you can, there are buttons or whatever, you can adjust this and you fix it just right. And then the temperature changes a little bit, or the supply voltage changes a little bit, or somebody sneezes, I don't know what, and it's going to be just a little bit off. So it works for a while, and then afterwards you see it drifts away, right? So how are we going to analyze this? Well, this, we're going to do this with superposition. Any sort of imperfect source, square wave. Sorry, if I write square wave, I write even fast, and you won't be able to read it anyway. So I just write SQ wave. Okay, so an imperfect square wave, something like this. I of t. So the imperfect one would be something like this. Make it a little bit really so that it's totally clear. I mean, hopefully it's not going to be that bad in the lab, but here you see, right? This is definitely not in the middle, and consequently it's going to go up much faster, and then it goes down very slowly, and we're not going to get back to zero if the times are the same. Okay, so we can actually split this up into two parts. We call this one here IDC. DC stands for direct current, but anyways, we mean this is a constant part. Doesn't change. And then on top of that, now we have the normal square wave that is perfectly balanced. This, of course, doesn't exist because there is going to be this IDC, and we don't even know exactly what IDC is. Ideally, it should be zero, but in practice, it's going to be a little bit positive, a little bit negative, and often it's even going to change. Sometimes it was positive for a while, and then again, for reasons I mentioned, we will get negative also. So what we model is I of t is equal to I square perfect plus plus IDC. Okay? It's going to be two pieces. Now, I square wave perfect, that's the situation that we analyzed last time, that we just looked up here again. We know the answer. The answer is we get exactly what we expect, right? This is perfect. The IDC, well, that is what's causing the problem. Now, if we analyze this whole thing with I of t, figure out what's going on the capacitor with I of t as the forcing current, it's going to be complicated. And it's easy to get confused. And the math gets tricky and everything. So is there a way, do we have something in our toolbox to simplify this problem, to make it easier? Yeah, I guess that was a hand supporting a hand. Back there? What could we use? When we have a circuit with lots of sources, what is the trick that we use to analyze this circuit that makes it easier? Yep. Superposition, precisely. We could think of this, of course, as two sources. We could think of this, let me maybe go and use another sheet of paper. We could think of this, this is page 4. I'm making this very colorful today. Page 4, we could think of it as our current source, I of t, that we connected to a circuit. We could think of that one as two current sources, I perfect of t, okay, plus IDC of t. Okay. So now we see it explicitly. We can think of this. I mean, in practice, of course, this is not the case. In practice, this is going to be one instrument that is just a combination, and there is no way to really separate the two pieces. But when we analyze things, we anyways use models. We use ideal resistors and ideal sources and so. Here we make a model that this models what's actually going on in the instrument that you have on your lab bench. Okay? can be split into the perfect part and the DC part. And again, we said already the perfect part, we analyze, that's the green line here that always happily goes exactly back to 0, and the DC part, well, that does something else. So, in particular, we can see that the DC part, why do I put my pen so far? The DC part is going to be Vc of t. Well, if we have a current, we analyzed this already, that we get that current gets integrated. But now, in the square wave part, at some point, the current changes sign and the voltage starts decreasing again. Basically, we're sucking now charges out of our capacitor. Well, with the IDC, it never changes sign, and so it just keeps going. Or, of course, IDC could be negative, and then it would look something like this. And the slope, again, we can't really say, because that's the whole point. We don't know what this IDC is. It's an imperfection. And heck, I mean, if we knew what it was exactly, we perhaps could eliminate it, but that, unfortunately, is not an option. Okay, so we need something that removes this charge that just gets accumulated to our capacitor. So let me redraw the circuit that we have. So we have, now we analyze only the DC part. So we have IDC, and we have this capacitor, which is our touch capacitor. Okay? And charge, just if you were to look at charge, would just accumulate on this capacitor indefinitely, and so the voltage just keeps going, right? I mean, until something, whatever. We don't need to worry about it. It's not going to work. So we need some simple thing to remove charge. Any ideas on how we could remove this charge from the capacitor? Yeah. Okay. We could have a switch here. And whenever, for example, we are at this point, we hadn't hit exactly 0, we simply close that switch, and then it's going to be 0 for sure, okay? And that's a perfectly fine solution. We could do that. In the lab, you're going to build this in the lab. The designers, they chose another solution, and there is good reasons why they chose another solution. This switch would add a lot of capacitance. Any switch you can buy is the switch. This is again is the switch plus a big capacitor like that. And that wouldn't be good, right? It basically masks our touch capacitance. Unless you have really big hands and fingers, we won't be able to detect any touch. So with the right technology and so on, we could do that. The other thing is you need a clock for that switch. So anyways, are there other ways to do this also? Simpler ways, actually. What is a simple element that certainly would suck out a little bit of charge continuously out of this capacitor? Yeah. Yeah, resistor. Why not? Let's try to put a resistor here. Or this is not RL for load, but RL for leak. So through this resistor, a little bit of charge continuously leaks away from the capacitor. Of course, if the charge was 0 on the capacitor, then there is no current flowing through the resistor either, which is perfectly fine. We're in the right spot already. But as the voltage on the capacitor gets large, more and more current flows, meaning more and more charge is removed from the capacitor. Likewise, it does the right thing. If for some reason the voltage on the capacitor gets negative, well, then the current in the resistor also changes sign, so it still removes charge. It's the right sign. So this is really neat. Simple, but hey, that's precisely the ticket. So where am I? 5. So now there is a little additional problem, and that is now suddenly we have a circuit that involves a capacitor and a resistor. And we know already the capacitor is modeled by a differential equation. So if you want to really solve this circuit, we're going to need a differential equation. And that's a topic of 16b. So we're not going to do that. We're going to do something else that is precisely in our toolbox from 16a, and that is these state transition matrices. We're not going to use a matrix here because it's just one variable. But you remember we had this thing. It was always something with Stanford. I remember that. It was something like how many people. Anyways, it was something like the variable x of k plus t, k plus 1 was equal to x of k plus some other stuff, maybe u of k or whatnot. Anyway, okay. So anyways, it was a method, state transitions that told us, well, given we have a system that is in a state at a certain time k, it told us what is the system in a state k plus 1. Okay? So basically what we're going to say is we assume that we know that what our system is in state k. We want to figure out what it's going to be in state k plus 1, and so on. And the distance between these two is going to be some time called t step. Okay? So time really is going to be equal. Time is going to be equal to k times t, or k plus 1 times t, and so on. Okay? So it's really this, we just write k, but what we really mean, time is equal to k times this, or k plus 1 times this t step. Okay, so so let's say that we knew the charge on the capacitor at time k. We want to now we want to derive an equation that tells us what the charge is on the capacitor at time k plus 1. So, and again, that time really is time 2 k plus 1 times t step. Okay? Well, this is going to be equal. The charge on the capacitor is still going to be there in the next step, plus the charge added by IDC minus the charge removed by this resistor. Okay? So this is going to be equal to QC of k, which we said we know, plus the charge that we add. Well, how much charge do we add? Well, we run a current IDC, and we run it for how long? Well, for t step, right? So this is going to be IDC times t step. That's the charge we're adding. And then we're also going to remove charge. Well, how much charge do we remove? Well, we're going to remove whatever charge flows through that resistor. What's the current flowing through the resistor? Well, that's the voltage across the resistor. Let's call this voltage here Vc of k, or k plus 1 times t. Right? So it's going to be equal to that voltage, Ohm's law, Vc of k over the resistance, or leak, times the time over which this current runs. Anybody sees a little hair in the soup? Okay, the little hair in the soup, I expected you to object. Hey, you make a big mistake. Okay, the hair in the soup is that the voltage across the resistor, of course, is going to change, right? So it's not quite correct what I wrote here. It's not V VC of K over R leak. It's some kind of an average between VC of K and VC of K plus 1. Okay, let's sweep this one under the rug. And here we have a good justification to do so. We can always make t-step very small. If we make the t-step very small, well, then the change in VC in every step is going to be tiny, and so the error we are making is very small. Incidentally, if you use a computer to solve numerically a differential equation or so, it does exactly this. So we haven't done something that, well, unfortunately didn't invent this, otherwise. First guy or at least the name attached to this is Euler, another Swiss guy, but he lived 1600 something, and so it's not me. Not my fault. I wish. Okay. So we can rewrite this equation a little bit. Let me conserve some papers and trees at least. So the next thing, we want to go from charge to voltage. We want to actually represent everything with voltages. We know that charge is equal to capacitance times voltage, so we need to simply divide by capacitance. Actually, it's the question mark in our system, right? Okay, so we're going to do that. We take the equation that we just derived, and we divide by C. So QC of K plus 1 now becomes VC of K plus 1 is equal to VC of K plus, let me write this, IDC minus VC of K over R leak, and times T step over C question mark. Okay? Okay? So, what apparently is happening now is that what this tells us that in every step we sort of retain what we had before, which is what we want. But then we have this additional term here, and we want to make this term to basically go to 0. And there is a little bit more analysis and so involved in this, but basically we want to make it that if here we add some charge delta Q, and here we remove some charge QR, we want that we remove at least as much charge, or we remove an amount of charge that is almost equal to the charge that we add. Okay. Now, doing this analysis gets a little bit tricky, so let's not get into this. One very good way to determine that is you just go and try in the lab different values of our leak, and you make sure that it always works reliably. Why would you not just make our leak a very small valued resistor? Yeah. Yeah, exactly. Then we get. Where do I have this? I must have this somewhere. Yeah. If we were to put a really large resistor here in parallel to the capacitor, instead of getting this the voltage that sort of increases here, it would just basically do this and would not increase almost at all, right? So we couldn't detect anything with that circuit anymore. So in practice, it's a bit of a trade-off. So we're going to first we make this IDC small, and then afterwards you choose a leak resistor that just makes it work. So you're going to build this in the lab, and you're not going to build a full touchscreen and so on. You can do that in your startup. But there are these two plates. You can see this copper tape, and you put your finger in between these, and then here is the circuit. It's got actually has three or four resistors, so there are a few. And it has this LED, and it has here another component. Anybody have an idea what that is? It's an operational amplifier. Yes, this thing is used to synthesize this current source that we need. Okay? So let's get going. Let's start with operational amplifiers. Yes. Oh, that's a loaded question. But when you need one, just buy the right thing. Just order a comparator, order an op-amp. In the lab, actually, this is something that I distinctly dislike. In the lab, you're actually going to use an op-amp as a comparator. And it sort of works. It's very slow. Now, the observer is a human in that particular case. You, right? And you know what? I have to tell you another truth about you. You are terribly slow. Compared to a computer or most electronic systems, you are terribly slow. So to you, it won't matter. It's going to be good enough. But in practice, usually we want, like for example, we want to scale this up to detect not only one touch sensor, but an entire array, a whole touch screen full of sensors. Do that, and you wait for half an hour. Seriously, you wait for half an hour until it's read out. Nobody would like that touch screen or phone, right? So they're different, but at some level they're somewhat similar. Okay? And if you really want to understand how it's different internally and why it's different and so on, I'd love to tell you, and of course I have a course on this, but there is a shortcut. Just come to my office hours and I'll tell you. Okay? But not here. Okay, so new topic, op-amps. And again, this stands for operation amplifier. Now, the important thing to make op-amps useful is a concept called feedback. And feedback is a very important thing. Engineers use it all the time, and it's very easy because you're all incredibly familiar with it. You use it all the time. So let's pick one example of where you're using feedback and where probably most of you are very aware of that. And it's the following situation. You have a car, could be a bicycle, but let's stick with the car for a moment. And you're driving this. You have to go down to Los Angeles for maybe Thanksgiving dinner or whatnot. And you want to go as fast as allowed, let's say 65, but not faster because you really cannot afford another speeding ticket. Okay? So, how are you going to deal with that? Well, your car, the essential part here of your car is a motor. Okay? And it has an accelerator pedal, and you press that, and then out of this comes the actual speed. Depending on how much or little you press the accelerator, the actual speed is going to be higher or slower. Okay? So then, you also, this is U. You are going to look at the speed signs. So you see that, for example, there is one of these 65 signs. You're going to compare that to the actual speed, which presumably you're going to read off of some, 0, 100 miles, and what's in the middle here? 40, 80, 120, and this one's 160. Okay? So you see that, for example, you see the needle somewhere up here. What do? You say, oops, I'm going too fast, and you let the accelerator pedal go a little bit. So basically here you calculate the difference, V delta, which is the desired speed, we desired minus the actual speed. You calculate that difference. If that difference actually is negative in this particular case, it would be 80. It would be 65 minus 80. Well, then that means you have to remove your foot from the pedal, okay? And likewise, if you find this situation, then you say, oops, I have to be careful, let me not fall asleep. But anyways, you're going to find that it's going to be 65 minus 40. You're going to press the accelerator pedal a little bit more, okay? And not surprising, this thing is called a feedback loop, okay? So there are few things that are important to realize about this feedback loop. One of them is the signs. If we go around this loop here, notice we go through this minus sign here, which makes this negative feedback. In EE16, we're always going to use negative feedback. Positive feedback is useful in some cases, but not here. In particular, imagine that you switch the plus and minus sign here in your car. You're going too fast, and you're going to go even faster. Not good. Don't try it. It could be detrimental to your health, even more so than your pocketbook. Okay, so we want negative feedback. So we're going to introduce some rules that ensure in EE16 we always have negative feedback. The other thing is this story about the motor. How powerful should that motor be? Ideally, if you had a choice. Let's forget gas mileage and stuff like that. How powerful a motor do you want to have? Exactly, infinitely fast. Infinitely fast, not because it sounds good, but why should the motor ideally be infinitely powerful? Yes. Yeah, but what does it really mean, not limited? Yes. Exactly. The answer was so that you can go at the desired speed as accurately as possible. When the motor is weak, it may work just fine in the flatlands, but the minute you hit the hill, you may have noticed that, then you just can't keep up. Okay? If you had an infinitely powerful motor, then no matter how steep the road is, you always will be able to go at the desired speed. Now, as a cyclist or tricyclist, I want to also point out one other thing, and that is, even if you have an infinitely powerful motor, that does not mean that you have to go infinitely fast. You still can go at any speed, all the way down to zero, okay? So an infinitely powerful motor is kind of the ideal thing. You can do precisely what you want to or what you should be doing. You can go exactly at the speed that you desire to go. That is the right speed. Okay? So ideally, and of course, I'm not turning this into a bicycle safety course or something like that. I have good reasons why we are talking about this infinitely powerful motor. Okay, so and we get to this in just a moment, but let's just make a sort of a conceptual model. So what we apparently have is we have a motor. I use a different symbol now. That, let's say, takes some power in, some input, and then some output, and that is going to be equal to the gain of the motor times the input. So this is A. Let me call this A, lowercase a, times x in, and this lowercase a, we want that to be infinitely powerful. Okay. So ideally, at least. I mean, in practice, you probably have to compromise a little bit, but not that much. So this is really the feedback system that we're dealing with. We have a block here, an amplifier called a motor in this particular case, that is infinitely powerful, meaning its gain AM is close to infinity or infinity. And then we have something that looks at looks at the desired, whatever it is, speed in our example with the car, and it looks at the actual speed, computes the difference here, this y delta, and accordingly adjusts the input to this box here to always make actually the difference between these two 0, right? That's what we want. In fact, if the motor is infinitely powerful, then we precisely have this situation that I delta is going to be equal to y desired minus y actual, and that is going to be equal to 0 for AM very large. Okay? But that's what we want. And the reason I say it like this is sometimes puzzling, but the puzzle comes on the next slide. So now we're going to do exactly the same thing, but now with an op-amp. An op-amp is a box that has two inputs, V plus and V minus. And these are node voltages. And then it has a box inside, like this. And the output is going to be equal to V out. It's going to be equal to AV, it's a voltage gain, times V plus minus V minus. Okay? And AV of the operation amplifier is going to be infinite, ideal. That's ideal. And in practice, the one in the lab, made the gain maybe only 100,000 or million or so. Let's not worry about that little difference, okay? You have to build extremely high gain circuits before that matters, and you will have other problems. Okay, so the operation amplifier also has a symbol. And this is the symbol for the operation amplifier. We simply put that funny little round box. Put that funny little round box to calculate the difference, sort of sweep that into the triangle. So here we have voltage V plus, here voltage V minus, and here voltage V out. And again, V out is going to be equal to AV times V plus minus V minus. A few other things about this, and AV is, so AV is infinite, and I plus is 0, and I minus is also 0. In other words, you don't need to give it any current whatsoever, it's just going to observe. If it's an ideal op-amp, it's going to observe the voltages V plus and V minus. It calculates the difference, amplifies them with an infinite gain AV, and it puts out an output voltage that is corresponding to that. And so also it's at the output, it's like an ideal voltage source. Just the value is a controlled source, a dependent source. They're not going to be on the midterm, okay? But you know. So here we have one, a dependent source. the value of the source is just given by this equation, and AV is infinite. Okay? Right? Are there any questions about this? Yes. I mean, just like in the mathematical sense, when you have a variable, the value of this variable is infinite. So when you do calculations, often then you sort of write A. You cannot write A equals infinity or so, but you can do this limits calculation. So what I mean is really that that value A is infinite. Okay. That's right. That's right. If V plus and V minus are not exactly equal, then V out would be infinity, which is a good justification that if we build our system right with an op-amp and negative feedback, then with the feedback, without feedback that may not be the case at all, but with feedback, and what I mean is negative feedback. So if we build a circuit like this one with negative feedback, with this op-amp, then V plus is equal to V minus. Okay? So assumptions for that is that the gain is infinite, that we have negative feedback. Okay? We did everything right. Yes. So, which is precisely again this thing. We will make big use of this, not only for calculations, but that's the whole point of it's just like when you're driving on the road, your cruise control makes it that you go at the speed that you tell it to. Okay, and for that it needs an infinitely powerful motor. And in cars you can get that, and they are gas guzzlers. With op-amps, it's actually a lot easier. You just buy a run-of-the-mill model, and the gain is like 1 million, and that's good enough. I mean, the error is negligible. Yes. No, because of this negative feedback, meaning that if this one increases, then this one here, because we subtract, is going to decrease. So this decreases, then that means that this one decreases. So again, when you do the calculation, so you convince yourself, you make AV a variable, okay? You make AV a variable, and you could make it 1,000 or something like that. Then you don't have this problem that you now have, if this is infinite, it's not something goes crazy, right? So then, in your calculation, you must have seen that in math classes. Then you go and say, now I look at what would happen to this equation if AV would go to infinity. Okay? And then you will either see the correct result or not. So that's how you do it. I mean, your thing is kind of, I sort of can see that. Why you would have this. In practice, of course, if this was only 1 million or so, then let's say you had a volt at the output here, you would have to have a difference of a microvolt, a millionth of a volt at the input, because if the gain is only 1 million. Right, so you see that if the gain here is finite, then this difference, then you get actually difference here. This voltage is a little bit different, and you get a little bit of an error. Therefore, right, you're not going at a speed that you desire. But if the gain is 1 million, the error is going to be like 1/1,000,000th of the desired speed. And if then you go and you make this mathematical sort of Limes approximation, then you find now the difference is actually 0. And as an engineer, you say that, of course, infinity exists only on paper, in a math paper, right? But as engineers, if the error is negligible, meaning that nobody would ever notice it, and maybe we cannot even measure it, it may as well be 0. Right? As engineers, we always do that. Because as engineers, this absolute correctness, as we have in math, where either the answer is correct or wrong, and if you are just 10 to the minus a million off, it's wrong, right? As engineers, we don't have that problem. As engineers, as long as it works under all circumstances and so on, then that's good enough, right? Now, of course, that turns out to be very hard also, but we're working on it, right? So op-amps. Okay, let's start with the first example of how we could use such an op-amp. So what we're going to do is actually precisely basically reenact this circuit diagram here. Okay? So we're going to build that thing now, but with an op-amp. So we have an input that is V desired. And we put this on the positive terminal, just like here, we put the desired input on the positive terminal. And then we get an output, V out. And then we take that, just like here, we stick it back into the negative terminal. And we call that V actual, which in this case is just equal to V out. Okay? So, maybe we could also have called this V in. So we have a circuit like this one, and this is V. Notice, by the way, that we have negative feedback, and for now at least, we simply determine that by, if we make a loop, and there is only one op-amp, keep it at that, then we go through the negative sign, not through the positive sign. Okay? So now we have this circuit. So we know what is V in. How could we figure out what V out is? But there are two ways. One of them is very easy. This is an ideal op-amp. We know V in, and therefore we know V desired. They are equal, right? Do we know what V actual is? Why not? If I call this V plus and this one V minus, would we know what V actual is? V plus equals V minus. V plus equals V in. V minus equals V minus equals V plus, and V plus equals V in. So V plus equals V in. V plus equals V minus. And V minus equals V out. Huh? V out equals V in. Okay? So an amplifier basically does the same thing as your car. You put in whatever voltage, the desired voltage, at the output you're guaranteed to get the same voltage. We'll talk in just a moment why this is useful. But now we're going to do what I hope will make your colleague back there happy. We're going to calculate another way. We're going to calculate with this Limes business, sort of like a mathematician. Okay? So V out is equal to AV times V plus minus V minus. Right? So that's the characteristic of an operation amplifier. Okay? So then V out, that's AV times V plus is equal to V in, and V minus V minus is equal to V out. Right? So consequently, we can calculate that V out is equal to V in times AV over AV plus 1. Right? So you can calculate that, what it would be, for example, if AV was equal to 10, which is a little bit less than infinity, by the way, then, this would be 10 over 11. That would be about 0.9, okay? It would be not quite exactly 1, right? But if AV would be 1,000,000, then this would be 1,000,000 divided by 1,000,000 plus 1. This is awfully close to 1, okay? I mean, you go and write down all the 9s. And now, if you make it this Limes calculation, you may have seen this. My nomenclature may make a mathematician cringe. But if you make AV go to infinity, AV divided by AV plus 1, what is infinity plus 1? It's pretty close to infinity. Okay, it's infinity, right? So then this is equal to V in. Okay? So now we have mathematically proven what we sort of intuitively saw all along. If the motor, or in this particular the amplifier, has infinite gain, then these two voltages here at the input are going to be the same. Provided, of course, you have negative feedback. And the reason I say that, in the lab, sometimes you hook up something wrong, and then it doesn't work like it's supposed to be. Well, this could be the reason. Okay? So we have a few more minutes to discuss why this would be useful. So what we have built is a circuit. Now let me sort of draw it correctly. We have a circuit that involves an operation amplifier. V out. And then it had this jog that goes back to the input. And let me draw it correctly this time. And we convinced ourselves that V out is equal to V in. Okay? We did this various ways, intuitively, and also this calculation, including this Limes AV goes to infinity. Is this thing useful? I mean, we have a voltage, let's say it's 1 volt, and then at the output we simply get 1 volt again. I mean, we had 1 volt already. How would this be useful? Anybody has an idea? Why could this be useful? Well, let's look at a situation. Let's say you have a microphone and you had a speaker. This one works always. I always laugh at this one. You have a microphone, you have a speaker. Let's say like here, I have a microphone and somewhere there is a speaker going. And you want to, whatever I put into this microphone, you want that to come out of the speaker. So you hook them together, right? No. Not surprising. So you have a microphone. Well, what would be a reasonable circuit model of a microphone? How would you model a microphone? As a voltage source, precisely. And it puts out the voltage V microphone, like this. And anybody has an idea of how we could model a speaker? Has anybody ever bought a speaker? Yeah? No? Nobody? It can, headset works too. Headset works too. But if you buy a speaker, don't they say this one is an 8 ohm speaker, and then there are other ones where they say it's a 4 ohm speaker? Anybody has seen that? No? You don't listen to music, right? What do you think? Anyways, a reasonable model for the speaker is our speaker, and for example, that could be 8 ohm. Okay, a typical value. Now you hook them together. But actually, the microphone, is this a reasonable model for the microphone? In other words, if the microphone output voltage is, let's say, 100 millivolts, can this microphone supply any current that you want to pull from it? Probably not, right? And so, have we developed some kind of a model? Do we have a model in our repertoire of sort of circuit models that models a source that is, not quite ideal, without making it too complicated? So a reasonable model for a circuit that is, for a source that is not ideal, without having to write 3 pages of description of what we mean. Yeah. Where could we put that? Anybody remember 7 in equivalence? Yes. Perfect. A voltage source with a resistor. Yes. So, our microphone is not an ideal voltage source, but we can model it as an ideal voltage source with an output resistance or a microphone that, let's say, is typically, something like 1 megohm. So, in other words, 10 to the 6th ohm. Okay? That would be sort of a reasonable model for our microphone. Okay, so let's say this V microphone, let's make our life easy, is 1 volt. What is V speaker? This is a midterm problem. Okay, so V speaker is going to be equal to V microphone times our speaker, that's 8 ohm, divided by 10 to the 6th ohm plus 8 ohm, which is like 8 micro. Do you think you're going to get a lot of sound out of that speaker? In fact, could we figure that out? Well, what is the power of the speaker? Now here there would be useful to use this expression. Right? Because we don't know the current, we could calculate it, but we just use Ohm's law in this equation. Okay, so V speaker, 8 micro, so that's 64 times 10 to the minus 12 divided by 8. So that's 8 times 10 to the minus 12 watts. This is a lot of power. Are you going to power the city of Berkeley when PG&E turns off the power? This is nothing. Undetectable. Forget it. Forget it. You're not going to get anything out of that thing. No beeps, no sound, no nothing. So, what if instead we had hooked up our microphone here and we hooked up our speaker over there? Let's try it. So, we have a new circuit now. We have our amplifier with negative feedback around it. And at the input, we put our microphone. And at the output, we put our speaker. The speaker. Okay? Now, first of all, what is the voltage here? Well, there is a resistor there. We have to ask ourselves the question, what's the voltage drop across this resistor? Now, I'm inclined to say this is another question that could very well be on the midterm. So even though today's lecture is not in scope, we actually do a lot of things that are precisely the preparation we need for the midterm. So how would you figure out what is this voltage here, V prime, or actually we call that V plus? Right? How will you figure that out? We have a resistor. What's the voltage across the resistor? Well, it's equal to the value of the resistor times something, a miracle. What is that miracle? The current. The current. So in this particular circuit, what is the current that is running through this resistor? Yes. 0. Why is it 0? Well, because we have said that this is an ideal op-amp, and then this current is 0. And this one, by the way, also. Okay? So then this current here is 0, and the voltage across here is 0, and V mu prime is going to be equal to V mu. Microphone voltage. Okay? So we can always, there can be a resistor there, but heck, if there is no current flowing, there's no voltage drop, so the nodes could even be just be connected together. Okay, so now, if this is an ideal operation amplifier, what is the voltage at this node here? This is going to be equal V mu also. Why? It's because V plus is equal to V minus. We have negative feedback here, and we have an ideal operation amplifier, then this is always true. So useful in analysis and also in understanding the circuit. This voltage here is 0. Okay? So that means that the voltage here is also V mu. That means that the voltage here is V mu. Right? The voltage across here is V mu. Okay? So it simply, a buffer simply replicates. And because this is an ideal operation amplifier, it can deliver however much current is needed. Okay? If the speaker needs 1,000 amps, the ideal operation amplifier is going to deliver 1,000 amps. So I want to say two more things. One is that this relationship, or here, I put it in the circuit diagram, I said that the voltage difference between the input terminals of an ideal operation amplifier is always 0. But this does not mean that there is a connection between these two terminals. So don't say, hey, the voltage 0, I could as well put this a short circuit, right? Don't put a short circuit there. If you do it in the lab, nothing works anymore. Okay? And if you do it on paper, then your calculation's probably going to get all messed up. Okay? So this is sort of there is a difference between the voltage at two nodes is the same, and two nodes are connected by a wire. This is not the same thing, okay? So don't somehow misinterpret this with, oh, I can put a wire in between there. Okay? I've warned you, because it always happens to a few people. Don't do it. Okay? So the other thing is kind of obvious, that this is an ideal operation amplifier, and therefore we could deliver 1,000 amps or whatever is required to this resistor. That little operation amplifier here, do you think it delivers 1,000 amps? No, just like any component, any practical component. This operation amplifier is probably going to be ideal in the sense that it can deliver currents up to maybe 100 milliamps, okay, 0.1 amps. Beyond that, it just shuts off. There's a protection circuit built into the thing that instead of it going into operational amplifier heaven, it simply turns itself off, okay? So you can actually, it's not easy to destroy these in the lab. You can, but It's not so straightforward. However, one thing, be careful if you make a misconnection or so. Some of these elements, let's say you connected the supply wrong or so, they can get pretty hot. So when I test the circuit, figure out that something is hot or so, touching things, what I do is, okay? Because now you have a little bit of water needs to evaporate. If it's hot, you notice and you pull away your finger instinctively right away. So it's just sort of little things to know in the lab. Before we break, I'll give you a puzzle. You can think about it at 10 o'clock after the midterm on Monday. And the puzzle is the following. Let me use another circuit. Another diagram. What's the current here? I is 0. What's the current here? I is 0. What's the current here? Well, it could be anything, right? Could be 1,000 amps or whatever. So we said that you take any component in the circuit. By the way, you better remember that for midterm 2. It applies. It's absolutely true. Yeah, and you add up all the currents that flow into the component, and that must be equal to all the currents that flow out of the component. So in this particular case, that would be I equals 0 plus I equals 0 equals I equals God knows what. So in other words, 0 plus 0 gets you anything. This is true for question mark equals 0, right? And for any other value of question mark, this is not true. So what in the world's going on? What is going on? Why are currents not conserved and therefore charge is not conserved in this operational amplifier? Yes. Okay. So what your colleagues threw out was complicated terms, VDD and VSS, also known as supply. This operation amplifier is not like a resistor. For it to do its stuff, you don't need to fill gasoline into it, but you need to hook up a supply, okay? It's not going to work without the supply. And now I'll tell you a little bit about the pitfall. When we draw circuits with operation amplifiers, when we draw the schematics, we pretty much never show these supplies. Okay? But in practice, there would be supply. So, be very careful. You draw the circuit diagram, it's got no supplies. Then you go to the lab and you don't hook up the supplies, and then nothing is going to work, I guarantee. Okay? So don't forget. Obviously, this makes, and you need to connect them to voltage sources. It makes the circuit diagram, showing these supplies in the circuit diagram makes it just about unreadable. So we never show them, but in the lab we put them there. Okay, thank you. And so good luck on Monday. You make me the biggest present by doing well on the midterm. Okay.
When we were talking about the negative feedback loop, and you said that V out is equal to this, how did you get this fraction?